after the break. I am a PhD student from Technical University of Delft and Utrecht University. And today we heard all about solid Earth deformation. And Terry actually gave a really quick show of what solid Earth can mean in projections. And yesterday was all about long-term and present day. So I will also focus on a projection today. So let's start off with this figure again, but in a different way. So I'll go a little bit deeper into this effect of glacial isostatic adjustment. And here in gray you see an ice sheet, and in brown you see the bedrock and the grounding line in position P1. So the Earth can roughly be divided in layers. In the top layer is elastic, and the layer below is a viscoelastic mantle. Then you have an ice sheet melting and a grounding line retreat from P1 to position P2. And this decrease in loading of the ice causes bedrock uplift. And with that, you can see that the grounding line actually advances back towards the ocean to position P3. And this grounding line effect that it advances is also decreasing the ice flux towards the ice shelf, and it's also lowering the sea level, which means in our setup of an ice sheet model that the ocean temperature at the base of the shelf would also differ and become a little bit cooler. So also the bedrock slope changes. So altogether, the bedrock uplift is a stabilizing effect, mostly via the grounding line. And the elastic layer gives a fast response, and the viscoelastic mantle gives a slow response. Now, when we look at projections that have been done until now, most of the projections for Antarctica use a constant bedrock topography over time, so that means that there's no GIA at all. But then there's also more recent studies that use the LRAM model, which is a two-layer flat Earth model with an elastic lithosphere and a uniform relaxation time that people set to 3,000 years, which is some sort of a global mean. But there's also one study from Coulon et al. That use a spatially varying relaxation time with the LRAM model. So there's a few of these. But the LRAM model is a simplification. So you can also use a spherical Earth that take into account different processes that's going on in the Earth. And here you see a depth profile of that at three different depths: 70 kilometer, 250 kilometer, and 400 kilometers inside the Earth. And in the top 70 would be, for example, elastic, and then below that there's a viscosity that people set to 10 to the power of 20 or 10 to the power of 21. But yesterday, we all learned that the Earth structure is not homogeneous, it's actually heterogeneous, and there is a big variation underneath Antarctica. And so we cannot measure viscosity from the Earth's mantle, because we can't go there. So we always need to approximate what could be the viscosity. And here you see two different profiles. So the magnitude differs, but the pattern stays the same when you vary different parameters to determine the viscosity. So let's dive a little bit deeper into one of them. In West Antarctica, already at 70 kilometers depth inside the mantle, you can see that the viscosity is quite low, which means that there is a viscoelastic delayed response, and the rest of East Antarctica, for example, is still responding elastic in that part. And then when you go deeper inside the Earth, for example, all the way at 400 kilometers, is already more homogeneous. So we can kind of correlate this to what would be the response time. And a very high viscosity have a response time of 150,000 years. But we can also see, for example, in West Antarctica, low viscosities that correspond to a response time of 50 years. This is dependent on the size of your changing ice sheet, but this is just a rough estimation. So there is, you can derive this from seismic observations, and then you can compute a mantle temperature. And then together with a stress, the grain size of mantle material and water content, we directly compute the strain rate, which is a little bit different from what we also heard before. Then we coupled this GIA model to an ice dynamic model, which is called IMAO ice. And this whole method will soon be online in the paper, but of course I'm happy to talk about the details of that, and I will skip it for now. So we are going to dive deeper into one projection now. We are doing projections using different IPCC scenarios and different global climate models, of which the forcing we got from Vio Coulon, and she will present projections with that forcing also later today. But for now, we focus on a very warm scenario with a very warm global climate model. And when we take a look at the sea level, so we only include the effect of the ice loading here. And then when you see the effect on the sea level contribution from Antarctica, then when you include no GIA, which is the blue line, the top line, we see that it's actually a higher sea level contribution than the black line below, which includes 3D GIA, because remember that this GIA is a stabilizing effect. And the red line shows the difference between the two, which is the highest at 2,400. So this also corresponds roughly to this response times that I just showed that we find in West Antarctica. So when we look at ice thickness, the differences are actually a lot larger. So there is, when you include no GIA, we look at the top row and we see ice thickness at 3 different steps in time, from 2,300 to 2,500. And we see an Antarctic collapse because the scenario is very warm. But then when you look at the difference between using 3D GIA or no GIA, we look at the second row, and the ice is actually up to 550 meters thicker when you include GIA. So this is because there is actually a bedrock uplift, which is shown in the lowest row of figures, when you include the 3D GIA of up to 25 meters in 500 years. So already at 2,400, we can see those effects. So these differences in ice thickness, of course, can have an impact on how stable is your ice sheet. And the grounding line position also differs with 100 kilometers. So coming to the conclusions, the sea level rise as a contribution from Antarctica is about 4% in 2100 and 7% in 2400, where it reaches its maximum. But then the local differences in ice thickness are up to 550 meters, and that has potentially could be important for the stability of the West Antarctic ice sheet. And we are working now with different global climate models, which actually vary quite a lot in the precipitation and the ocean temperature. So we will also find a different GIA response. And in lower scenarios, for example, there could be less warming, where the timing of the grounding line position is more important, where the GIA could have also a bigger effect. And we're testing multiple 3D Earth structures, so I'm really happy to continue the discussion later with any of you. Thank you.
Awesome talk. Thanks very much. And brilliant timing. You've got heaps of opportunity for questions. So we'll start with a really difficult one. Oh, any questions?
Thanks a lot for the talk. So if I quoted correctly, you said it's 25 meters in 500 years, right? Do you have a sense what are observational errors for the bed topography right now?
Sorry, for?
What is the magnitude of errors, which is the observed bed topography under the present-day ice sheet is?
The uplift rates at present day, you mean, or?
No, I mean the errors to measure what is the bed elevation under the ice sheet is.
Ah, from the GPS? I don't...
From bed machine, whatever you use in your numerical model, you put the bed.
I use bed machine, yes.
Do you have a sense?
But I don't know the exact error bar, no.
Well, I'll tell you.
Oh, yeah, thank you.
On the order of 50 to 150 meters.
Yes.
So, my question is, what is the kind of impact of your contribution from changing GIA compared to the quality of the knowledge of bed topography right now?
Right, I see your question. So the goal of this is to do a sensitivity study between using different GIA models. So we always start off with the same bedrock topography, and we will see the difference from there. So we assume, okay, this is the bedrock topography, and look only at the differences. So that's why, yeah, we think it's valuable.
Awesome. Are there any other questions?
Thank you for the nice talk, Carolyn. I'm going to ask you, but this is a question really for all the GIA modelers that are here. You know, even your 3D models don't begin to replicate what we're actually measuring in the Amundsen embayment, which is 5 centimeters a year of uplift, which is 500 meters in 100 years, right? Much higher than actually what you're simulating. And I wonder if you have thoughts on that discrepancy and where it's coming from.
Yeah. When you compare, these simulations are under a very warm scenario, but the ice sheet model is initialized to present-day ice thickness and volume, for example, but it's not initialized for ongoing GIA. So we are testing now from an equilibrium state, because at the moment there are no published results from coupled 3D GIA projections for Antarctica. So we are starting step by step from an equilibrium model.
Great, thanks, Caroline. We'll move on to our next speaker, who is Frank Patton.